Our fact for today is that rockets have to go faster than 7 miles every second or 25,000 miles per hour in order to get into space. We call this the escape velocity. If they do not reach that speed, those objects will be pulled back down to the surface of the Earth because of gravity. Now, the moon, you only have to go 5,300 miles per hour in order to get off the surface of the moon and reach an escape velocity. We're going to find out through the lesson today why there is such a difference between the escape velocities for the Earth and the moon. Now, I just want to let you know that you are starting Jedi training today. We are going to be looking at field forces. Basically, these are forces that act through a distance on objects, and we will be learning lots of interesting ways to use these forces in order to move objects without touching them. So our standard is that forces between objects act when objects are in direct contact, which is what we talked about with the pushes and pulls, when you're actually touching the object, and also when they are not touching. This would be the field forces that we're about to start learning about today. The I can statements, I can explain how the force of gravity is affected by the mass of the object and the distances between them, and the difference between mass and weight. So here we have some people you're probably familiar with. We have Wile E. Coyote and we have the Roadrunner. We're going to real quick watch a little video clip of the Wile E. Coyote who's always trying to catch the Roadrunner. Now, in usual form, the Wile E. Coyote goes running off the cliff. Notice he doesn't fall right away. His forward movement due to inertia is overcoming that pull of gravity until something stops him. He's acted on by an unbalanced force, and now gravity takes over and he is pulled to the surface of the Earth. So again, gravity is what is pulling him down. The idea of gravity was pretty much labeled by Isaac Newton. He was an English scientist in the late 1600s. He kind of realized that gravity is occurring everywhere. He used the idea of gravity to explain why the moon orbits the Earth. He used observations that he made through telescopes to come up with why the moon orbited the way it does. He also has his 3 laws of motion. We've already discussed those in our previous unit. And today we're going to talk about the universal law of gravity. The universal law of gravity basically says that all objects in the universe are attracted to each other through gravitational force. So right now, look around the room and see who is near you. Even though you're not being pulled and hitting the person next to you, everything around you, every person, every pencil, every pen, every piece of paper, the walls, the floor, the ceiling, everything is pulling right now on you. But there is one object that's pulling with more gravitational force than any other object. Take a minute and see if you can figure out what that object might be. I'll give you a hint. It's very big and it's extremely close. If you guessed the Earth, you're right. The Earth is pulling with more force than anything else. And if you don't believe me, drop your pencil. Where did it go? It went down to the floor. Now, if the floor wasn't there, where would it go? It'd go down onto the first floor. Imagine there was a hole dug underneath and it fell into the hole. It would fall to the bottom of the hole. What if that hole was deeper? It would fall even deeper. So gravity is always pulling everything to the center of the Earth. Hopefully you saw that yesterday or last week on the gravity pitch gizmo. Here on the screen, we have the universal law of gravity. The force of gravitational attraction is equal to this constant times the masses of the 2 objects multiplied together divided by the distance between the objects. So as you can see, mass is going to affect the amount of gravitational pull, and the distance between the objects is going to affect the amount of gravitational pull or attraction between 2 objects. So gravity is just defined as the attractive force between 2 objects. Again, everything around you is pulling on you with some force, but it's dependent upon the mass of the objects and the distance between them. So we think of the Earth as being this big, huge planet, but in actuality, it's very small compared to the sun. So technically, the sun should pull on us with more force than the Earth does. But the problem is the sun is 93 million miles away. The Earth is right here. So it's that combination of the distance and the mass of the objects. So if you have more mass, then there's more gravitational pull. Less mass, less gravitational pull. Now, if you put the objects closer together, they have more gravitational pull. And if you pull them apart, you have less gravitational pull. So closer together is more, further apart is less. So here's a quick question. Who has more gravitational force based on just their masses? Big football player or tiny gymnast? Well, the big football player has more mass, so he would have more gravitational pull. Now, when we look at the distance between the objects, we're going to get some help from our friend Grover. Hopefully you didn't think this was Elmo. This is Grover. He's going to show us near and far. So right now he's far away.
This is far!
So he has less gravitational pull. As he comes closer to us, he now has more gravitational pull.
You see?
Now notice his mass is not changing, just the distance between us and Grover is changing. If that mass is staying the same when he is closer, he has more gravitational pull, and when he's farther away, he has less gravitational pull. Now, a gravitational field is basically just the force field that exists in the space around every mass or group of masses. So even though you're sitting here and not being pulled towards all these people around you, there is a gravitational field around you and around everything that is around you, nearby you. Now, it goes in all directions, but if you get things further away, then you have less gravitational force. Now, we measure this in newtons per kilogram in this gravitational field. Some gravitational fields that you're probably familiar with is the Earth and the Moon. The Moon is pulling on the Earth and the Earth is pulling on the Moon. Luckily, the Moon is traveling at just the right speed that it is constantly moving slightly ahead in its orbit to overcome that pull of gravity to pull it back to the Earth. But if it were to slow down, gravity would overcome the forward motion and it would pull the Moon to the Earth's surface. If the Moon were to speed up, it would overcome that pull of gravity and fly off into space. We also have satellites that go around the Earth. Same thing. We have to get them going just the right speed so that they stay into orbit. So they're balancing with that pull of gravity. Otherwise, they would fly off if they were going too fast, or they would be pulled back down to the surface of the Earth if they were going slower. Now, if you look at these weights for the apple, the closer to the surface you are, the more that apple is going to weigh. As you increase the distance between the apple and the Earth, the weight is going to change. And we're going to find out the difference between mass and weight because they are not the same thing. Remember from the gravity pitch gizmo, the gravity is pulling everything to the center. This is why if you are a penguin down in Antarctica and your feather drops, it doesn't go down relative to the people on the top of the Earth. It falls back to the surface of the Earth, which when you look at it on a globe is actually in the upward direction to the people that are standing on the top of the globe, maybe at the North Pole. Gravity is pulling everything to the center. This is a very distinct difference between mass and weight. A lot of times they're taught as being interchangeable, but they actually mean two different things. If I wanted to have the best weight loss plan in the universe, I could. Within 3 days, I could make you weigh 1/6 of what you do now. What I would need to do, the secret to this miracle weight loss, would be to put somebody into a rocket and fly them to the moon. On the moon, you weigh 1/6 of what you weigh on the Earth. The problem is you don't look any different. Your mass stayed the same, but your weight changed. Mass is defined as the amount of matter in an object, how much stuff there is. Weight, on the other hand, is the gravitational force acting on the object. So let's see the difference between mass and weight in a real life situation. Here's a picture of my daughter when she was about half the age she is now. She weighed about 68 pounds this day when I took her to, it was a natural history museum in New York City. If that 68-pound person were on the sun, she would weigh 1,447 pounds. But she doesn't look any different. Her mass stayed the same. Her weight is a lot more. Let's say we take her to Mars. Instead of weighing 68 pounds on Mars, she weighs only 17 pounds. But look at her. Her mass stayed the same. The amount of matter in her body stayed the same. Let's put her on the moon. She weighs just 9.6 pounds. Again, her mass has not changed. She still has the same amount of stuff that makes her up. But her weight, because it's determined by the gravitational pull, is going to change. Now, this I thought was kind of interesting. If we put her on a neutron star, and this is what's left after the big stars go kaboom, if they're not big enough to go into a black hole, they will turn into neutron stars after they blow up in what's called a supernova. You look at it, it says 0.827 pounds. Now, that doesn't look real interesting until you see what it says right under the number. That's in trillion pounds. So if you were to take her 68-pound weight on the Earth, and that mass gets transferred to a neutron star, she weighs 827 billion pounds. That's a lot. Now, I heard it once said that a teaspoonful of a neutron star has more mass than a cruise ship filled with people. It's a very, very tightly packed star. Very, very dense. Now, because you weigh 1/6 on the moon, theoretically, if you could jump 1 foot high on the Earth, you could jump 6 feet high on the moon. This is why if you've ever seen the videos of the astronauts walking around on the moon, they usually hop and jump. It's a very efficient mode of transportation. Now, how do these gravity facts affect animals and plants and the adaptations that have occurred? Well, if you live on land, you have to have a strong skeleton in order to support against the force of gravity. This is why plant cells have to have a cell wall in order to support them. Like a tree has to have those cell walls around each of its cells, otherwise it would not be able to support the very, very high trees. Water animals don't have to have those strong skeletons because the water actually balances some of that downward pull of gravity. So there are a lot of things that live in water that don't have to have those skeletons, either exoskeletons or endoskeletons. Now, our question at the beginning was, rockets have to go faster than 25,000 miles per hour to get into space, but on the moon it's only 5,300 miles per hour. Why? Why is